All right, so get this. We're diving into the world of neutrinos today.
Oh, neutrinos.
Yeah, you might not be a physicist,
Okay.
but trust me, this is going to be mind-bending, even if you just enjoy, sciencey stuff.
Right.
Okay, so picture this.
Okay.
A particle so tiny, so ghost-like, it can pass through the entire Earth like it's nothing.
Really?
That's a neutrino.
Wow.
And guess what? They are literally everywhere. Like you're being bombarded by them right now.
That's kind of freaky.
I know, right?
Yeah.
So you're probably thinking, why should I care about something I can't even see?
Yeah. Exactly.
Well, that's where our expert comes in. They're going to help us unpack
Yeah.
why these little ghosts are actually huge news in physics.
So what's really fascinating about neutrinos
Okay.
is that they basically mess with our whole understanding of how the universe works. They're like subatomic particles, way smaller than atoms.
Right.
And for the longest time, we thought, okay, they're massless, no big deal.
Mm-hmm.
And then, boom, experiments show us they actually do have mass.
Oh, wow.
It's just incredibly tiny.
Mm.
And figuring out exactly how much mass they have is one of the biggest head scratchers in physics right now.
So it's like, how do you even measure something like that?
Right.
Like, what are we talking? Like, trying to weigh a feather in a hurricane?
It's a pretty good analogy because it's that difficult to pin down.
But why is knowing their mass, like the exact number, such a big deal?
Okay, think of it this way.
Okay.
The standard model of particle physics,
Yeah.
it's basically our rule book for the universe at its tiniest level.
Mm-hmm.
And for decades, it worked great. Explain how particles interact and all that.
Right.
But the fact that neutrinos have mass
Yeah.
that wasn't in the rule book,
Oh.
it's like finding a glitch in the system.
Okay.
It tells us there's something more to the universe.
More than we even know?
Exactly, more than we currently understand.
Okay, I'm starting to see why we can't ignore these little guys. But if they're so tiny and they barely interact with anything, how do we even know they're there?
That's where scientists get really creative.
Okay.
We've built these incredible detectors. I'm talking massive contraptions,
Wow.
all designed to catch the faintest hint of a neutrino interaction.
Oh, wow.
Take IceCube, for example.
Okay. IceCube.
It's literally a cubic kilometer of ice in Antarctica.
Wait, hold on. A cubic kilometer of ice.
Yep,
You're burying a giant detector in the ice.
pretty much.
Why Antarctica?
Well, the ice acts as a filter. It blocks out other particles,
I see.
which could mess with our readings.
Right.
So when a neutrino, and it's a rare event,
Yeah.
but when it does interact with the ice, it produces a tiny flash of light.
Okay.
And the detectors pick up on that light.
Ah.
And we can actually trace the neutrino's path.
So it's like a giant frozen telescope.
That's a great way to put it.
But instead of looking at stars, we're looking for these like fleeting particles.
Exactly.
Pretty impressive. But I'm guessing IceCube isn't the only trick up their sleeve.
Oh, absolutely not.
Okay.
There's another amazing detector. It's called Super-Kamiokande.
Super-Kamiokande.
It's in Japan.
Okay.
Picture this. A giant tank filled with ultra-pure water.
Okay.
And it's surrounded by thousands of light sensors.
Wow.
Similar principle to IceCube,
Yeah.
waiting for that flash of light when a neutrino interacts with the water molecules.
Okay, so we're talking huge, elaborate setups just to catch a glimpse of these things.
Yeah, it takes some serious dedication.
But it must be worth it.
Oh, absolutely.
What kind of discoveries have they led to?
Well, besides confirming that neutrinos do have mass,
Right.
they've revealed something even more bizarre.
Oh, that's that.
Neutrino oscillations.
Neutrino oscillations. Okay.
See, there are actually 3 types of neutrinos.
Okay.
Electron, muon, and tau,
Okay. 3 types.
each linked to a heavier partner particle.
Okay.
And get this, neutrinos can change between these types as they travel.
Wait, so they're like shapeshifters.
Exactly.
They morph from one form to another mid-flight.
It's pretty wild.
Hold on. So a neutrino can start as an electron neutrino
Yeah.
and then suddenly decide, I'm a muon neutrino now.
Happens all the time.
What triggers this identity crisis?
That is the million-dollar question.
All right.
And it's tied to the mystery of their mass.
Okay.
The fact that they can oscillate,
Yeah.
that's the proof they must have mass,
Okay.
even if it's incredibly small.
So how does that work?
Well, the theory is that the mass difference between the 3 types, that's what drives this shape-shifting behavior.
So by studying these oscillations, we're not just seeing a cool neutrino trick.
Right?
We're actually getting closer to understanding the fundamental nature of these particles
Exactly.
and why their mass is such a puzzle.
You got it.
It's like they're leaving us clues if we can just figure out how to read them.
That's a great way to put it.
So speaking of clues, where did these neutrinos even come from in the first place?
Oh, that's the exciting part.
Okay.
We're talking about cosmic origins.
We're going cosmic.
Yeah.
Tell me more.
One of the most dramatic sources,
Yeah.
supernovae.
Supernovae.
The explosive death of massive stars.
Oh.
These events are so powerful, they blast neutrinos out across the universe.
So those tiny particles we're struggling to detect here,
Yep.
they were born in the heart of a dying star.
It's mind-blowing, right?
It's like they're time capsules carrying messages from these cataclysmic events across, like, billions of light years.
Exactly.
Incredible.
And it's not just supernovae.
Yep.
Our sun is a constant source of neutrinos, too.
Our sun.
Yep, the fusion happening in its core, the process that powers the sun.
Yeah.
It's a neutrino factory.
Huh?
And these solar neutrinos give us a unique window into the heart of our star.
Wait, so we're using neutrinos to study the sun's core,
Exactly.
the place we can't even see directly.
Right. It's like having X-ray vision for a star.
That's pretty ingenious.
Well, they barely interact with anything, right?
Yeah, that's what I thought. So how do they escape the sun's gravity?
That's exactly what makes them such valuable messengers.
Yeah.
Because they interact so weakly with matter, they zip right out of the sun's core.
Ah, I see.
They're like tiny spies.
Carrying information.
Exactly. Giving us a glimpse into a world we can't see.
Okay, I'm starting to get why these neutrinos are such a big deal.
Yeah.
They're not just some esoteric particle.
Yeah.
They're giving us insights into how stars work, how the universe evolved, and maybe even the laws of physics themselves.
You're getting it.
It's amazing.
It is.
But we haven't even touched on one of the most fascinating areas,
And
right?
you're talking about sterile neutrinos.
Sterile neutrinos, yeah, what are those?
Well, that's the story for our next segment.
Okay, now you've really got me hooked, listeners. Don't go anywhere. Things are about to get even wilder in part 2 of our neutrino deep dive.
It's going to be good.
I can't wait. All right, so we're back and ready to really get into these neutrinos. Before the break, you mentioned sterile neutrinos.
Oh, yeah.
Sounds like things are about to get even weirder.
It might.
What makes them so sterile?
Okay, well, remember how we were talking about regular neutrinos?
Yeah.
They're already like goads, barely interacting with anything.
Right.
Sterile neutrinos take that to a whole other level.
Okay.
Remember the weak force, one of the fundamental forces of nature?
Yeah, you explained it like a handshake between particles.
Exactly.
And regular neutrinos, they participate, but reluctantly.
Yeah, they're not big on socializing.
So sterile neutrinos, but they just ignore everyone?
Pretty much, they wouldn't even bother with the handshake.
Really?
Yeah, they'd mainly interact through gravity, which is super weak at the subatomic level.
So wait, we're talking about a potential 4th type of neutrino.
Potentially, yeah.
And it's even more elusive than the 3 we already know about.
That's the idea.
Why even bother looking for something that might not even exist?
Well, that's the beauty of science, right? We're driven by the unknown.
Right.
The possibility of finding something totally groundbreaking.
I see.
And there are these hints, these anomalies in some experiments
Okay.
that we can't explain with our current neutrino knowledge.
So maybe sterile neutrinos are the missing piece.
They could be.
It's like having a shadow you can't catch.
Yeah.
But you see its effects.
Exactly.
Tantalizing.
Very.
But how do scientists even start looking for something so elusive?
One way is to look for signs that they're oscillating with regular neutrinos.
Oh, okay, like the shape-shifting.
Exactly.
But with an extra invisible dancer.
You got it.
What kind of experiments are looking for these phantom dancers?
There's the Novier experiment, for example.
Okay.
They use a powerful beam of neutrinos,
Okay.
send them on a journey over hundreds of miles.
Wow.
And by studying how they oscillate along the way,
Yeah.
they're hoping to see something unexpected.
That would point to sterile neutrinos.
Right.
So it's like sending these neutrinos on a road trip
I like that analogy.
and looking for any side trips they might take.
Exactly.
What other tools are in the neutrino hunter's kit?
Well, another strategy is to just build even bigger, more sensitive detectors.
Okay.
Think IceCube, but supersized.
IceCube, but big.
Way bigger. IceCube Gen 2, it's in the works.
Okay.
It'll be 10 times larger than the current IceCube.
10 times.
Yeah, massive.
It seems like this search is pushing the limits of everything.
It is. It's cutting-edge science and technology.
But let's say we find them.
Okay.
What would that mean for our understanding of the universe?
That's where things get really interesting.
Okay.
Because sterile neutrinos, with their unique properties,
Yeah.
they're a prime candidate for dark matter.
Hold on, dark matter. Like the mysterious stuff that makes up most of the universe.
The one and only.
Are you saying these stealthy neutrinos could be the answer to the dark matter puzzle?
It's a possibility.
That's huge.
It is a big deal.
But why sterile neutrinos specifically?
Well, they don't interact with the weak force, right?
Yeah, right.
Right.
So they wouldn't emit light
Okay.
or interact with regular matter the way we expect,
I see.
which fits with what we know about dark matter. It's elusive.
Right. We can't see it.
Exactly.
And they could be heavier than regular neutrinos, right?
Much heavier, potentially.
So that could explain why dark matter has such a strong gravitational pull.
On galaxies, yeah.
So finding sterile neutrinos wouldn't just solve a neutrino mystery.
Nope.
It could change our whole understanding of the universe.
Look, it's a game changer.
It's like we've been searching for a missing ingredient all along.
And it might have been right under our noses.
But passing right through them.
Exactly.
But apart from dark matter, what other implications could there be?
Well, they could also point to new physics beyond the standard model.
Like a whole new set of rules.
Potentially, yeah.
Wow.
Their existence would suggest there are forces and interactions happening that we don't even know about.
Like a hidden chapter in the universe's rule book.
A good way to put it.
Okay, I'm convinced.
Sterile neutrinos, if they exist, are a game changer.
Absolutely.
It's amazing to think that these tiny, almost undetectable particles could hold the key to some of the biggest mysteries in the universe.
It's pretty mind-blowing.
But even if we don't find them, just the search itself is incredible.
Oh, definitely.
It's pushing the boundaries of science and technology,
Leading to new discoveries along the way.
like exploring uncharted territory.
Exactly.
You never know what you might find.
That's the spirit.
So let's shift gears a bit.
Okay.
Back to the neutrinos we know for sure are out there.
All right.
The electron, muon, and tau neutrinos.
The regulars.
Even without sterile neutrinos, they're helping us answer some big questions, right?
Absolutely.
Like, what can these little ghosts tell us about the grand scheme of things?
Well, remember those supernovae we were talking about?
Yeah, the exploding stars.
The massive ones.
Right, they blast neutrinos across the universe.
Like little messengers.
But how do we decode those messages?
By studying the neutrinos they emit, we can learn more about what happens during those explosions.
During these super powerful events.
Exactly. And these events are crucial.
For what?
For creating heavy elements, the building blocks of, well, everything.
Like planets and, us.
Exactly. The elements that make up you and me were forged in those explosions.
So these neutrinos, they're like carrying blueprints for the universe.
In a way, yeah.
They hold the secrets to how everything came to be.
It's pretty amazing.
It's mind-blowing.
And it's not just about the past.
Okay.
Remember how we talked about solar neutrinos?
From the sun.
Right, and how they tell us about the sun's core?
Yeah, like X-ray vision.
Well, by studying the changes in the solar neutrinos we receive,
Okay.
we can actually track changes in the sun's core over time.
Wait, so we can monitor the sun's, heartbeat?
In a sense. Yeah,
Just by listening to these neutrinos.
You got it.
That's incredible.
And important too,
Why?
because the sun's activity affects us here on Earth.
Right, like with our climate and stuff.
Exactly.
Wow, these neutrinos are really versatile.
They are.
They're giving us glimpses into the past, helping us understand the present, and maybe even giving us clues about the future.
They're pretty amazing particles.
But I have a feeling we're not done yet.
You have a good feeling.
There's one more aspect of neutrinos you wanted to talk about.
Oh, yeah, there is.
Something about hidden dimensions and new forces of nature.
You remember?
I do.
That's a conversation for our final part.
Okay, now you're really speaking my language. Don't go anywhere, listeners.
Huh.
Things are about to get even more mind-bending in part 3 of our neutrino adventure. Okay, so we're back for the final part of our neutrino journey. And you've really got me intrigued with this whole hidden dimensions thing.
It's where things get really interesting.
New forces of nature, it sounds almost like science fiction.
Well, it's kind of where the cutting edge of physics meets, the really mind-boggling stuff.
Right.
So we know about the 4 fundamental forces of the universe, right?
Yeah, gravity, electromagnetism, and the strong and weak forces.
Exactly. But some physicists think there might be even more.
More forces?
Forces we haven't even discovered yet.
Okay, so like a whole secret level to the universe.
That's a good way to put it.
Operating on rules we don't even know.
Exactly. And some theories suggest that neutrinos,
Wow.
with their weird behavior and tiny masses,
Yeah.
could be interacting with these hidden forces.
So they're like giving us a peek into this hidden world.
Potentially, yeah.
Wow, so these tiny, almost invisible particles
Right.
could be our portal to like a whole other universe.
It's a pretty wild idea.
It's mind-blowing. But how do you even begin to look for something that exists in dimensions we can't even perceive?
It's a challenge, but not impossible.
Okay.
One way is to look for indirect evidence.
Indirect evidence, okay.
Remember those neutrino oscillations we've been talking about?
Yeah, the shape-shifting.
Right. Well, if neutrinos are interacting with forces in hidden dimensions, it could subtly affect their oscillations,
Ah, I see.
creating patterns we wouldn't expect based on our current models.
So it's like those hidden dimensions are creating ripples in the neutrino pond.
I like that analogy.
And we can analyze those ripples to figure out what's going on.
Exactly.
That's pretty cool.
That's why experiments like NOVA and IceCube are so important.
Right, they're not just looking for sterile neutrinos.
Nope, they're looking for any weirdness in the neutrino data.
Any hints of new physics.
Exactly.
It's amazing to think that these massive detectors buried underground or in ice could be our windows into, well, everything.
Not just the universe we know, but maybe even beyond.
It's pretty humbling, actually.
It is.
Well, this has been an incredible journey.
I'm glad you enjoyed.
And I'm a little sad to see it end, but I'm definitely walking away with a new appreciation for these tiny, mysterious particles.
They are pretty amazing.
Zipping through us all the time, carrying secrets from who knows where.
And that's the beauty of science, isn't it?
What's that?
It's a never-ending quest for knowledge.
Always exploring.
Exactly. And who knows what other mysteries neutrinos will unlock in the future.
Maybe we'll find even more types of neutrinos.
Or figure out dark matter and dark energy.
Or maybe even prove those hidden dimensions exist.
The possibilities are endless.
I'm officially a neutrino enthusiast now.
Welcome to the club.
This has been an incredible deep dive, and thanks for being such a great guide through this fascinating world.
The pleasure was all mine.
And to our listeners, even though we can't see them, feel them, or even really understand them, neutrinos are out there.
Constantly reminding us that the universe is full of wonders.
Beautifully said. Well, that wraps up our deep dive into the world of neutrinos.
Hope you learned something new.
For sure. And to our listeners, check out the show notes for links to some of the experiments we talked about and other resources to keep you exploring.
Keep those brains buzzing.
Until next time, keep looking up, keep asking questions, and keep exploring the universe.
And all its hidden wonders.
See you next time.